Now let's understand how compound interest works and the mechanisms involved. In compound interest, as we are already aware, whatever is the amount that I'm borrowing at the beginning of 1 year, at the end of the year, interest is calculated on that and added to it. And this new principal plus interest becomes the principal for the next accounting period or compounding period, and then again I'll be charged interest on that. So let's take the example of at the end of this year, today, right here, right now, I borrow I rupees. 1 year later, I have to pay back r% of I as the interest. So that would be I plus r% of I, or if I take I common, that would be I into 1 plus r by 100. You can also look at it from a percentages point of view. An amount I which is borrowed is increased by r% and paid back. So at the end of 1 year, exactly 1 year, it becomes I into 1 plus r by 100. And should I not pay back this amount, I into 1 plus r by 100 becomes my principal for the next year, right? So that's equivalent to, forget the previous story. If I borrow I into 1 plus r by 100, the rate of interest r% for 1 year, I'll have to pay I into 1 plus r by 100 into 1 plus r by 100, right? Because this quantity I'd like to increase by r%. So at the end of 2 years, I'll owe I into 1 plus r by 100 whole square. So until at the end of n years, I'll owe I into 1 plus r by 100 whole power n, right? So what else can be observed? At the end of the first year, I owe a into 1 plus r by 100. Second year, I owe p into 1 plus r by 100. At the end of the second year, I owe p into 1 plus r by 100 whole square. Third year, I owe p into 1 plus r by 100 whole cube, and so on. What does it tell me? Amount to be repaid in compound interest at the end of each year happens to be in a GP. P into 1. If I look at this term as k, at the end of the first year, I owe pk, next year pk square, next year pk cube, and so on till p into k power n for the n years. Other than that, if I also look at this as, at the end of the first year, I owe p into 1 plus r by 100. At the end of the second year, I owe p into 1 plus r by 100 whole square, which means, what is the interest for the second year? For the first year, it was p into 1 plus r by 100. Remember, this is cumulative. P into 1 plus r by 100 whole square is the amount at the end of the second year. That includes interest for the first year and second year. First year, my principal was p. P became p into 1 plus r by 100, which means my interest for the first year was pr by 100. Now, my principal for the second year was p into 1 plus r by 100, which became p into 1 plus r by 100 whole square. I will get my interest for the second year by calculating amount at the end of second year minus principal for the second year, which will be p into 1 plus r by 100 into 1 plus r by 100 minus 1, which is p into r by 100 into 1 plus r by 100. Similarly, for the third year, right, amount for the second year becomes principal for the third year, which would be p into 1 plus r by 100 whole square, and amount at the end of third year will be p into 1 plus r by 100 whole cube. So interest for this period again would be pr by 100 into 1 plus r by 100 whole square. As I can see, interest for the first year is pr by 100, interest for the second year is pr by 100 into 1 plus r by 100, interest for the third year is pr by 100 into 1 plus r by 100 whole square, and so on. Therefore, I can generalize this and say interest for the nth year would be pr by 100 into 1 plus r by 100 whole power n minus 1, which is interest for the nth year, not interest for n years. Interest for n years would be p into 1 plus r by 100 whole power n minus p. Amount at the end of n years minus principal gives me interest for n years. First year, second year, third year, all of them put together. Interest for the nth year would be p into r by 100 into 1 plus r by 100 whole power n minus 1. As you can see, interest for subsequent years is also in a GP. P r by 100 into this square, into so on. Let's look at a question in compound interest. If an amount lent at compound interest becomes thrice of itself in 8 years, in how many years will it become 27 times of itself? What I'm being told is p into 1 plus r whole power n is equal to 3p, where n is 8, because the amount becomes thrice of itself in 8 years. Now, 1 plus r whole power 8 is 3. Now, in how many years will it become 27 times of itself? It will become 27 times of itself when p into 1 plus r whole power, I don't know how many years, is 27p, right? Which means 1 plus r whole power something should be 27. That will only happen when I cube both sides. When I cube this, I have 1 plus r whole power 24 is equal to 27. Therefore, I can say in 24 years, the amount becomes 27 times of itself. Alternately, as I know that amounts in compound interest are always in a geometric progression, in a cycle of 8 years, the first 8 years, p becomes 3p, which means in the next 8 years, 3p becomes 3p into 3, which is 9p, and in the next 8 years, 9p becomes 27p. So even that way, I can directly say 8, 8, 8. In a period of 3 such cycles, 1 becomes 3, 3 becomes 9, 9 becomes 27. So I can directly say that in 24 years, the amount would become 27 times of itself. Let's look at installment-based questions in compound interest. If a loan of 1,05,000 is to be repaid in 2 equal annual installments, interest being compounded annually at 10% per annum, how much is each installment? Now, we can do it in 2 ways. One following the cash flow model and one following the discount and net present value model. We'll do the first thing. We borrow the loan today and the amount that is borrowed is 1,05,000. Now at the end of year 1, we pay an installment I, and at the end of year 2, we pay another installment I, and thereby the amount remaining is 0. We settle the entire debt, or we really pay back the entire loan, right? So 1,05,000 is the amount that is borrowed. At the end of 1 year, at 10% per annum, how much does it become? 1,05,000 into 1.1, right? Which is 1,15,500, right? Now, of this amount, I borrowed so much at the end of the 1 year, I owe him 1,15,500. Of this amount, an amount of I has already been paid, which means now my principal for the next year is not really 1,15,500, but 1,15,500 minus whatever I paid already. Now, on this amount, I'll be charging an interest of 10%, right? And this is the amount that I'm going to pay at the end of 2 years. Is that clear? Look at it once again. I borrow an amount of 1,05,000 today. At the end of 1 year, simply we look at it 1 year at a time. I owe him 10% plus this, right? Which means I owe 10% plus 1,05,000, which is nothing but 1,15,500. Now, of this outstanding amount, an installment I has been paid. Therefore, 1,15,500 minus I becomes my principal for the next duration. For the next duration, I'll be again paying 10% as interest. So 10% plus principal would be 1.1 times my new principal, right? It should be 1,15,500 into 1.1 minus 1.1 into I when I carry it to the other side. I plus 1.1 I would be 2.1 I. Therefore, I is equal to 1,15,500 into 1.1 by 2.1. Remember, this is 1,05,000 into 1.1 into 1.1 by 2.1. 2.1 goes 50,000 times in it. 1.1 into 1.1 is 1.21. 1.21 into 50,000 is 60,000. 500 rupees. So now the whole question is, how much is each installment worth? Each installment is worth 60,500. Now when you think of it, the original amount that I borrowed was only 1,05,000, but I ended up paying 60,500 plus 60,500, which is 1,21,000. I'm paying the additional 16,000 as the interest for the 2 years, obviously. Some of it I'm paying at the end of this year itself, some of it I'm paying at the end of 2 years. So that's how we calculate EMI using the cash flow method. Instead of this, alternately, if I want to follow the present value method, now before getting there, we need to understand what present value is. Let's say I invest 100 rupees today. At the end of 1 year, at the prevailing rate of 10% per annum, I deserve to get back 110 rupees. Now, let's say I don't even invest it today. 100 today would be 100 next year. Now, don't you think because of inflation or whatever reasons, the value of rupee deflates over time? Right? Now, that is to say, 10 rupees today is not the same as 10 rupees next year. If someone borrows 1 lakh today and he says he'll give me back 1 lakh rupees next year, I'm not fine with that, right? I want him to pay me 1 lakh plus 10% or whatever is the prevailing rate next year. That's the least I expect. If I'm not a money lender or someone, that's the least I really expect, right? That is to say, money at different points of time is not worth the same. 100 today is not the same as 100 next year, or 100 1 year from now, or 100 10 years from now. It has different values, right? So, 100 today, right, is how much 1 year later? 100 into 1.1. So now, drawing the reverse analogy of that, 100 next year is worth only 100 by 1.1 today. That is to say, if you borrow my 100 rupees and you say you'll pay 100 rupees next year, I'll say no, 100 next year is worth only 100 by 1.1 or 90.9 next year. If you borrow 100 today, you better pay me 100 into 1.1. So this process from now to the future is called compounding, from the future to the present is called discounting. So let's think like the money lender. He says, lend you 1,05,000 rupees today. Now, you're going to pay me 2 installments, of which 1 installment I'm going to receive after 1 year, right? Now, if I pay you the money today, at the end of 1 year, I expect I into 1.1. But you're paying me 1 year later. You're paying me an amount I 1 year later. Therefore, today its worth is only 1 point. I by 1.1. From now to the future, multiply by 1.1. From the future back to the present, divide by 1.1. Similarly, now the second part, another I also you're going to pay me, but you're going to pay me at the end of 2 years. If I lend you I today, I expect 1.219 2 years later. Now, if you pay me I 2 years later, what's its value today? That's only I by 1.1 square or 1.21 today. Now, the present value of the future cash, you're paying me I 1 year from now, I 2 years from now. This I today is worth only I by 1.1. This I today is worth only I by 1.21. Now, 1,05,000 is equal to, when I take the denominator 1.21, 1.1 into 1.1, that's 1.1 I less I, which is 2.1 I. I is equal to 1,05,000 into 1.21 divided by 2.1. This is 50,000, and 50,000 into 1.21 is 60,500. As you can see, we got exactly the same answer. But the utility of this method is, while calculating EMIs for many months, this method becomes a lot more useful. Let's say I'm not talking about 2 months, I'm talking about 10 months. I'm talking about lending a principal B. Let's say rate of interest is 10%, and I plan to pay it back in 10 annual installments, equal annual installment. I'm paying it, and the first installment I pay at the end of the first year is worth only I by 1.1 today. I'm discounting it for 1 year. The second installment I pay is only worth I by 1.1 whole square today, I by 1.1 cube, I by 1.1 power 4, and so on. So until I by 1.1 whole power 10. Now, which is nothing but, if I take I common, 1.1 power 9 plus 1.1 power 8 plus so on till 1 divided by 1.1 power 10. Now, I can say I is equal to P into 1.1 whole power 10 divided by 1 plus 1.1 plus 1.1 square plus 1 till 1.1 whole power 9. Now, as you can see, your denominator is nothing but a geometric progression. P into 1.1 whole power 10 divided by 1.1 whole power 10 minus 1 by 1.1 minus 1, which is 0.1. This is nothing but, if you remember, a plus ar square plus 1 till a into r power n minus 1. Sum of n terms of a GP is a into r power n minus 1 by r minus 1. That's what exactly I've applied here. A plus ar square plus 1 till a into r power n minus 1 is a into 1 into r power n minus 1, 1.1 power 10 minus 1 by 1.1 minus 1, which is 0.1. So this directly lets me calculate each EMI if I'm talking about 10 equal annual installments. Now, the first method would not have been very ideal here, because calculating P for 1 year and then P into 1.1, and then from that subtracting I, and then calculating interest on 1.1 P minus I each time would have been very cumbersome and next to impossible. Now, I can apply this method whether I'm talking about 10 months, 50 months, or whatever. Now, if I'm talking about a 50-month EMI, it would be 1.1 power 50 by 1.1 power 50 minus 1 into 0.1. Simple. Just by changing this value of n, I can get any number of months or any number of years that I seek, and that really makes it useful on a day-to-day basis.